This video covers the analysis of the chained hash table. Last time we defined all the operations and we got part of the way through analyzing the data structure. Now we want to finish that off. So remember that many of the chained hash table operations take big O of L time, where L is defined to be the expected length of a bucket. What we need to do in order to have a more conventional efficiency class in terms of n is analyze what this L is related to n. N is the number of pairs actually in the hash table. I'm going to claim that the expected value of L is big O of 1. We're going to see why that is briefly. And if that's the case, then these hash table operations are big O of 1 expected time. First, let's look at the very worst case scenario. So the worst possible situation is when all of the keys collide. It's unlikely to happen, but it could happen. So that means that for every possible key we ever insert, our hash function gives the exact same index. In my sketch here, it's this one in the middle here. And so every single key in this whole hash table went into the same bucket, and I've got one big long linked list that has all of the pairs in it. So that one bucket has length big O of n, and then that big O of L runtime becomes big O of n time, because anytime we loop through this list, we have to visit all n elements. So searching would involve evaluating the hash function, decide on an index, but we always pick the same index, and then you have to loop through every single pair in the whole linked list. So if this happens, our hash table kind of devolved into a linked list. It's not really benefiting at all from the hash function or the vector here. This whole array vector is just a waste of space, really, and the hashing is also a waste of time. If we were okay with this, we should just have a plain old singly linked list. So that's the worst possible scenario, but it's kind of unlikely. Now let's look at a more likely scenario and work out what the expected value of the length of one of these buckets is. So here's the lemma that we're going to prove. The lemma says in a chained hash table using a universal hash function and with n less than or equal to m, the expected length L of any bucket is at most 2. So this is saying that the expected length of one of those buckets is 2. On average, we expect one of those linked lists to have 2 pairs in it. So here we go. Let's see why that's the case. So let's let x be an arbitrary key in the table, and set S is the set of all keys aside from x. So x is one of the keys, S is all of the keys that aren't x. And let's define an indicator variable, capital I subscript y. I'm going to call this IY, where for any y in S, so this is an indicator that could be true or false for any of the keys other than x. IY is 1 when x and y collide, or 0 otherwise. So if y is a key that collides with x, then IY has the value 1. If y is a key that does not collide with x, IY has a value of 0. We're using a universal hash function, so we know that the probability that any IY is 1 over m. That's the rare collision property of universal hash functions. And so the expected value of IY would be this probability that IY is 1 multiplied by 1, and that multiplied by 1 just disappears. So the expected value of IY is 1 over m. X's bucket contains x plus any other keys that collide with x, right? So the linked list that x is in has x for sure, and then if there's any other keys that collide with x, those are in that list as well. So the expected value of L, the length of that list, would be 1 for x itself, plus if we sum over every y in S, so if we add up for every other key that's not x, this indicator value, IY. And now we're going to manipulate this expected value expression. So the expected value of 1 is just 1. We can distribute the expected value there. It's not a random value. And the expected value of this summation, we can distribute the expectation inside the sum. So we have 1 plus the summation for every y in S of the expected value of IY. And then we just said that the expected value of any IY is 1 over m. So we have this sum of all these 1 over m terms, and there's n minus 1 of them. So this expression here simplifies to 1 plus n minus 1 times 1 over m. There's n minus 1 keys that aren't x, and each one of them has a chance of colliding of 1 over m. And so we can simplify that a little bit. Just instead of having multiply by 1 over m, just make it a fraction. So we have 1 plus n minus 1 over m. And this n minus 1 over m term is strictly less than n over m. We're just kind of cleaning up the notation there a little bit. So the expected length of L is less than 1 plus n divided by m. By assumption n is less than or equal to m, we're going to keep m, the size of the vector, greater than or equal to the number of pairs in the hash table. So if we do some algebra there, divide both sides by m, the fraction n divided by m is less than or equal to 1. And that says that this expression here, EL, is strictly less than 1 plus n over m. And if we substitute in 1 for the n over m term, we have 1 plus 1, which makes 2. So what does that mean? The takeaway is that if L is the expected length of a bucket, the expected length of a bucket is 2, and 2 is big O of 1. That's a fixed constant. So anything that takes big O of L time, we can actually say takes constant expected time. Therefore, the chained hash table operations contains, find, insert, and erase all take constant expected time. This is faster than AVL trees. We went through AVL trees. They take log n time for these operations, and we've seen that log n is a very fast performance, and AVL trees are fast, don't get me wrong, but hash tables are even faster than that. They take constant time for all of these operations. So constant time is a pretty great efficiency class. That's the same speed regardless of n, and this is really remarkable. That means no matter how big the hash table is, it takes about the same amount of time to search, insert, or erase elements. So these have perfect scalability. No matter how many elements you're dealing with, they're about equally fast. If you have a small hash table with 5 elements in it, or a big one with several million elements in it, same speed, no slowdown as n gets bigger. So here's the summary of the asymptotic efficiency of these operations. The constructor that creates an empty hash table is constant time. There's no qualifiers there, so that means constant worst case time. All of the rest have this expected situation. So the contains operation takes constant expected time because on average the chain length is constant, but in the absolute worst case scenario, it's linear time, big O of n worst case time. And that same pattern holds for the rest of these operations. Find has the same runtime. Insert has basically the same runtime except it's constant amortized expected time because on an insert, there's the expected qualifier from the random length of the bucket, and then there's the amortized qualifier because of the fact that we might need to resize occasionally, but really constant time. But again, big O of n worst case time. If you have to do a resize, or if we're in the worst case scenario with the collisions all in one bucket, linear time. Erase has the same runtime. Erasing an element is constant expected time or linear worst case time.